Good morning. Today we're going to be working on 6-1 and 6-2. 6-2 is pretty much just an extension of 6-1, so I decided just to do it in the same video. The thing that we're really looking for today is patterns, lots and lots of patterns. What we want to see is where we're noticing the same things happening and start to make some hypotheses and determine if those hypotheses are correct. So what we're going to start with is what we know about quadratic functions. So these are both in, if we look at both of these are in vertex form or graphing form of the equation. The first one has a negative a value, which means we know it's going to open down. So let's go ahead and graph that. This has an hk of -3, 4. Remember that h is always the opposite of what you think. K is always exactly what you think it would be. So -3, +4, we're going to graph that point. Because a is negative, instead of going out 1 and up 1 like we normally would, we're going to go out 1 and down 1 in both directions. From that point, we're going to go out 1 and down 3 in both directions, out 1 and down 5 in both directions. Remember that particular pattern, that's for parabolas only. So we have an a of -1 and we have a starting, so the end behavior is really what's happening on the right side. So the starting direction is down and the end direction is down. It's down because a is negative. Some people prefer to think of this as increasing and then decreasing. That is fine if you want to use those words. Otherwise, you can just describe it in the way that the arrows are pointing, both down in this particular case. On the second one, we have an a of 2, and we have an hk of 3, -2. So we're going to graph the point 3, -2. And then instead of going out 1 and up 1, we're going to go out 1 and up 2, because a always tells us what to do after we go right 1 from the locator point. And then out 1 and up, instead of 3, we're going to go 6 because of that a = 2. So here we have both ends pointing up, and we have an a of +2. So up and up. So what we find, or what we know, or can hypothesize at this point, is that if a is negative, we end down. If a is positive, we end up. The next thing we want to work on is getting our equations from vertex form into standard form, so all the way multiplied out. Biggest thing here is making sure that you are careful about where to do everything, which to do where. So a lot of people want to distribute this negative into the parentheses. You can't do that because our order of operations says we have to deal with parentheses, then exponents, then multiplication, then addition. And this technically I would say is multiplication. So the first thing we need to do, because we can't do anything with the inside of our parentheses, is do our exponent. So we're going to take x + 3 squared, x + 3 times x + 3. If we multiply that out, that's the FOIL method. So we do x squared plus 3x plus 3x, that's where that 6x comes from, plus 9. Then we need to keep that in parentheses, distribute our -1 into that. So -1 gives times x squared gives us -x squared. -1 times 6x gives us -6x. And -1 times 9 gives us -9. And then we drop down that +4. So simplified, -x squared minus 6x minus 5. So let's go ahead and do that with our one here. I'm going to leave a little space on the side. So the first thing we need to do is x minus 3 times x minus 3. Some people are more comfortable with the box, so I'll do a quick re-demonstration of that. X minus 3 times x minus 3. X times x gives us x squared. X times -3 gives us -3x. X times -3 also gives us -3x. And -3 times -3 gives us a +9. These two are like terms. So -3.
I'm sorry. I'm afraid I don't have an answer.
Sorry, my phone blipped apparently. I said something that woke up scary. So negative 3x plus negative 3x gives us a negative 6x. So if I wrote just this part in standard form, it would be x squared minus 6x plus 9. So I'm going to go ahead and put this back over here, y equals 2, and then in parentheses, x squared minus 6x plus 9, and then minus 2. I'm going to go ahead and distribute that first 2. So y equals 2, x squared minus 12x plus 18 minus 2. I can combine 18 and negative 2 here. So my standard form, x squared minus 12x, whoops, plus 16. So something to note about this is that at the beginning, we started with, actually I'll come back here. There we go. At the beginning, we started here with an a value of negative 1. Here, it's the same value. A is negative 1. Here, a is 2. Down here, a is also 2. So when we go from the standard form, from the graphing form, a does not change. Going the other direction, standard form to factored form, this is the process we're looking at here. All of these are negative, which means we can factor out a negative 1. So when we factor that out, basically we're doing a greatest common factor here. So if I multiplied this back out, I'd have negative 1x minus 6x minus 5, which is what it's supposed to be. So then I take this part right here, and I factor that. And if you need to, you can use box and diamond for that. X squared, 5x squared, 6x from the middle, 5x and 1x give us 6x. So x plus 1 and x plus 5. So that's our factored form with that negative 1 dropping down and staying out in the front. So when we look at the second equation here, each of these are divisible by 2, so we factor out a 2. So we have 2. We always want to look for that greatest common factor when we're going to factored form. So then we just need to factor this x squared minus 6x plus 8. Again, box and diamond if you need it. Not everybody does. Zoom in a little bit there. So x squared, 8, 8x squared, negative 6x. We have factors of 8 of 1 and 8 and 2 and 4, and that's all of them. Since they multiply to give us a positive and add to give us a negative, everything needs to be negative. So negative 2x, negative 4x adds to negative 6x. So x minus 4, x minus 2. Something to point out here is if I had gone here from that point and factored, I'm going to show you what would have happened with that. It would have been essentially the same idea. We just would have had to been more careful. So 2x squared, 16, end up with 32x squared on the top and negative 12x squared on the bottom. Factors of 32 are 1 and 32, 2 and 16, not divisible by 3, 4 and 8. I think that's it. Again, negative, because they multiply to positive and add to a negative. So I'm going to use negative 4x and negative 8x. So here's where it's tricky, because normally we can only divide out the 2 in a certain spot, but here we could divide the 2 out either way. And that's where we have to be careful. So if I divide the 2 out over here, 2x times x gives me 2x squared. X times negative 8 gives me negative 8x. And 2x times negative 2 gives me negative 4. I double check that negative 2 times negative 8 gives me 16. So I have a factored form of 2x minus 8 times x minus 2. But that is not fully factored because if I look at 2x minus 8, that has a greatest common factor of 2. So I can take a 2 out of that, and I'd have x minus 4 on the inside and x minus 2. So if I don't recognize that greatest common factor initially and factor it out here, then you have to factor it out at the end and check for a greatest common factor so that you still have that a hanging out front of 2. Okay, so back to, let's get that out of the way, sorry. Back to that 2. Sorry, trying to get those out of the frame. Now that we're in factored form, we can find our x-intercepts. So we use the zero product property for this. The zero product property tells us that if we're multiplying things together and they equal 0, then at least one of them has to be 0. We are multiplying our factors x plus 5 times x plus 1. The reason that they equal 0 is because, the reason our y equals 0 is because everywhere along the x-axis, so there's our x-axis, everywhere along there, if I go to the point -1, 0, 1, 0, 2, 0, -2, 0, all of those points have a y value of 0. So that's why we can put in 0 for that y value and use the zero product property. So we take each of our factors, x plus 5, set it equal to 0. That's not a very good one, but x plus 1 equals 0. Subtract 5, subtract 5, subtract 1, subtract 1. So we have x equals -5 and x equals -1. So our roots, or our x-intercept, and you'll hear those interchangeably, you'll most likely hear roots more than anything on these videos, are going to be -5, 0 and -1, 0. Our other example, we do the same thing. We take that x minus 4 equals 0, x minus 2 equals 0. So we have plus 4, plus 4, plus 2, and plus 2. So x equals 4 and x equals 2. So 4, 0, 2, 0. So that kind of brings us all together to a lot of the stuff we need to know about factored form, standard form, how to go between them, and how to find those x-intercepts. So once we multiply out in standard form, so far we know 3 different degree polynomials. First degree, which is linear, second degree, which is quadratic, and third degree, which is cubic. We haven't used the cubic in this form, but that's the form that we're going to use. Polynomials are always in that form, ax to the n, with descending, so the number of the exponent going down until it's 0. The coefficients, a, b, c, etc., can be any real number, but the exponents have to be a positive whole number, a positive integer. So all these numbers are going to be a positive whole number. Today, or not today, but for this first part, we're just dealing with the quadratic and the cubic to see what type of roots they create. In just a moment, we're going to get into higher degrees. So whatever we call the exponent is called our multiplicity, and that can determine what type of root we have. So if we look at graphing x minus 1 squared, we know that this is a parabola with an hk of 1, 0 because of this plus 0 that would be out here that we don't see. So we go to 1, 0. We're going to go up 1 and over 1 in both directions, up 1, out 1, and up 3, and we make our parabola. So this type of root, where it just touches and then changes directions, where it just touches the x-axis, changes direction, that is called a bouncing root. That's an informal term, but it's used pretty commonly. Our cubic, we know this one has the hk of -2, 0, and we know it's cubic because of that. If we think back to our parent graph stuff, we're going to -2, 0, up 1 and over 1, back 1 and down 1, and this has this little point of inflection right here. You can't see where I'm pointing, right there. So when we have a root that has that little wiggle, we call it a flat root. Again, informally. Some teachers will call it a wiggle. Some will actually call it the point of inflection. But whenever it doesn't go straight through, that is called a flat root. It doesn't technically go flat, just to mention that. But it does kind of straighten out that concavity changes from here to here. So it's important to know the names of that. And what we notice from that, or hopefully notice for people who went through the investigation, is that when we have even roots, even multiplicity, so 2, 4, 6, 8, we end up with bouncing roots on that factor. When we have odd multiplicity that's not 1, we end up with a flat root or a wiggle root or a point of inflection at the x-intercept. The ones that we had, the previous one, where we had, and I wouldn't go back because it doesn't work, where we just had a parabola where it's crossing, those are just simple roots where it's only crossing through there. So even though this changes direction, it's not on the x-axis and it's not a root. So the fact that it's just crossing through here, those are simple roots. So those are our 3 types: bouncing, flat, and just crossing or simple roots. Final direction is down. Okay, so knowing that, you can use Desmos. I'm not going to because I don't really need to. One thing I want to point out with these when we graph them is we don't really care about how high or low on the y-axis this is going. We really only care right now about what's happening at the x-axis. When we start getting into higher degrees, those can go really, really, really high, so way up off the graph, way off down the graph. We really don't care where they turn around, just what they're doing at the x-axis. All right, so x minus 3 times x plus 1 times x minus 5. Each of these are a factor. X minus 3 is a factor. The root associated with that factor is going to be a positive 3. And that's going to be a simple root because it has no exponent. It has just a multiplicity of 1. X plus 1 is going to have a root at -1, 0. And that's all zero product property stuff. Also simple. And x minus 5 will also be simple. That's going to have a root at 5, 0. The a value, if there's nothing out here, that's just an a value of 1. If there was a negative, it would be an a value of -1. I'm not going to worry about the start behavior right now, but the end behavior, because a is positive, is going to be up. So what I'm going to do is I'm going to graph my 3 roots at 3, 0, -1, 0, and 5, 0. And what I'm going to do is I'm going to start with my arrow going up. And I'm going to go from the back, and I'm going to cross through, turn it around to cross back through, turn it around to cross back through. Because all those are simple roots, that's all I want it to do. The next one, I have an a value of -1, which I know means my end behavior is going to be down. Now, people do this in a lot of different ways. This is what works for me, so that's how I'm teaching it. But if something else, you figure out something else that works better for you, then by all means, use it. So my roots here, x minus 1 squared, that's going to be that factor of x minus 1 squared is going to have a root of 1, 0. And it's going to be a bouncing root because of that squared. X plus 4, that factor is going to have a root of -4, 0, and that's just going to be simple because there is no exponent on it. So let's go ahead and put in those roots. This is 1, 0. That I'm going to put a b by it to remind me to bounce it. And -4 is just going to be simple. I also know this end behavior is going to be down, so I'm going to start low, a bounce here, so turn it around, and I'm going to have to turn it around to come back up through there. I did forget to mention over here, my start was down, pointing down. So one thing to be careful about when you're doing this, make sure you don't add other roots just because you want to turn it around. I tend to find that when trying to work out my starting direction, I just tend to confuse myself. So I think for me, it's better to note the roots and what types they are, and then start at the end direction that I know based on what A is. So we're going to generalize these things a little bit. Hopefully, if you did the investigation, you'd figure this out on your own. My factor is x minus 3. That means I'm going to have a root at positive 3, 0. The multiplicity on that is just 1, so that is a simple root. So just crossing. X plus 3 is going to have a root of negative 3, 0. If that is even multiplicity, so to the second, to the fourth, to the sixth, that's going to be a bouncing root. If I have nothing inside with the x, my root is just going to be 0, because if I plug in 0 for x, that would make it 0. If it's odd multiplicity and it's not 1, so just to add that, not 1, then it's going to be a flat root, or a wiggle root, or whatever you want to call that. That point of inflection is going to be on the x-axis. Moving over to end behavior, I'm just going to do a couple things here. If A is positive, then my end behavior is up. Whoops. If A is negative, my end behavior is down. My final direction is down. If I have odd multiplicity, If I have even multiplicity, so the first and the third one here both have even multiplicity, then my start and end arrows are the same direction, up and up or down and down. If I have odd multiplicity in my leading term, I'll explain that in a moment. If my end behavior is up, if my final direction is up, my starting direction is down. And if my final direction is down, my starting direction is up. So when it talks about leading term, that is whatever your first term would be if it's in standard form, and we're going to talk more about that in a moment. So we get into higher degree polynomials in 6-2, and we're looking at these are all in standard form, and so our leading term is the one that has the highest exponent. So 8 here, 5 here, 7 here, 3 here, 2 here. Most of the time, those exponents will be in order from highest to lowest, so 5, 3, 2. So the important thing to notice is if they're not, but most of the time they will be. So my leading term here is x to the 7th. That means my degree is 7. Here, my highest exponent is x to the 5th. My leading term is negative x to the 5th. My degree is 5. Here, 4x to the 8th is my leading term, and the degree is 8. So the highest exponent, the term with the highest exponent, if I'm in standard form, is my leading term, and then my degree is whatever that exponent is. If I'm in factored form, I have to do a little bit more thinking about it. So my A in all of these is already factored out, so that's helpful. Then I need to look at what my leading term would be if I multiplied everything out. That doesn't mean I have to multiply everything out. That just means that if I were to multiply this, the most number of times that I would be multiplying x by itself is twice, x times x. So 3 would be my coefficient, my leading coefficient, and then x to the second is going to be my leading term, 3x to the second, which makes my degree 2. Here I have 1x times x again times x again. That's going to give me x to the third with my a value of 5, 5x to the third, degree 3. Here I have x minus 7 squared, which means in that one I'm going to be multiplying x by itself twice. Here I'm going to do that 3 more times and then 1 more time. So 2, 5, 6. So my leading term is going to have a of negative 2, x to the 6th, with a degree 6. If I multiplied this out, this would be a much longer polynomial, but when I'm in this form, I can just kind of count up the number of times I'd multiply x by itself. 3 is going to be my leading coefficient here. That's a really lousy 3. There we go. I multiply x by itself once here, twice here, and 5 times here. So 5, 6, 7, 8 times. So this is going to be a leading term of 3x to the 8th with a degree 8. Once here, once here, once here, and once here. So 1, 2, 3, and 4. I have no a value other than 1, so that would be 1x to the 4th, or just x to the 4th with a degree of 4. A doesn't always have to be a whole number. I have negative 0.2 here. That's going to be my leading term, or my leading coefficient. I have x to the 3rd, x to the 4th, and then 9 more times, so x to the 13th. So this is going to be negative 0.2 x to the 13th, and I have that as a 13-degree polynomial. So in Desmos, or if you use Desmos for this one, I'm going to pause and see if I can bring that up or not. Okay, I haven't tried this before, so I'll be curious to see how this works. So I have x to the 4th minus 21 x squared. Whoops, didn't get that one in there. 21 x squared plus 20x. So, nope, not 2x, 20x. No, 20. There we go. Okay, so if I look at this, I've got a root at -5, a root at 0, a root at 1, and a root at 4. My end behavior is up, which I know should be the case because my a value is 1. So let's see if I can shrink this down. There we go. So then I'm just going to sketch that graph. I had -5, 0, 1, and 4. End behavior was up. They were all, whoops. Those were all simple roots. So I just need to cross through. So that gives me a leading term of x to the 4th, a degree of 4. Starting and ending behavior is both up. We'll do one more. Whoops. We'll do one more with Desmos, and then we should be able to work this out from patterns because I don't think we have any other ones in standard form. So negative 0.1 x times x plus 4 to the 3rd. So it shouldn't be terribly, this one is in factored form, so it shouldn't be too surprising to us. We've got a negative a, so our in direction is down. We've got x as one of our factors, which means we're going to have a crossing root at 0. And then we have x plus 4 to the 3rd for one of our factors, so we're going to have a root at -4 that is a flat root. So let's get rid of Desmos. No, not that one. Okay, and go ahead and graph that. So 0, -4. We know our end direction is down, and we know -4 is going to be a flat root. So end direction down, cross through at 0, come back, and flatten it out at -4. A leading term is -0.1. Our degree is 4, and we are starting and ending both down. And that kind of thing we should know from our other patterns that we've seen so far. Sorry, our leading term here would have been x to -0.1 x to the 4th. I only wrote the leading coefficient there. Okay, let's zoom in a little bit on this next one. Okay, so we've got an n direction that's up because a is just 0.5. We have a bouncing root at -3 because of that factor. So I'm going to put a b by that. We have a crossing root at -1 because of the x plus 1 factor. We also have a crossing root at +1 because of the x minus 1 factor. And then we have a root at -5 because of that x plus 5. We know our n direction is up. All of them are crossing roots except for -3. So I'm going to cross, turn it around, cross again, turn it around, and then come down, bounce here, and go down. We should have an odd degree here. So this is 2, 3, 4, and 5 because they're going in opposite directions, or they're starting and ending in opposite directions. So this would be 0.5x to the 5th. It's a 5th degree polynomial. Start direction is down, end direction is up. We add a little bit more in here with the next one. We know our end direction is going to be down because of that negative. We know we're going to have a root at 0 because of the x right there. X minus 3 squared means we're going to have a +3 root. That's going to be a bouncing root. X minus 1 means we're going to have a crossing root at 1. And x plus 2 means we're going to have a crossing root at -2. So if our end direction is down, we're going to start down here, bounce, turn it around to cross, turn it around to cross, turn it around to cross. So opposite start and end direction, which is good because we have 1, 2, 3, 4, 5 degrees on this one. We'd have a leading term of -0.5 x to the 5th, so degree 5. If you've gotten the point by now, you can probably end this video. You don't have to watch the rest, but in case you want to. X to the 6th, we're going to have a bouncing root at 0, a bouncing root at +4. So those are both bounces. As they get bigger, as those exponents get bigger, they do flatten out a bit more, but they're still considered bouncing roots because of the direction change. I know my end direction is going to be up because that is a positive number. A is positive. So this is a degree of 8. If it's even, both my start and end are going to be up. So I'm going to start up, follow it down and bounce, turn it around to come back and bounce again, and back up. Here I've got a negative here, so I know my end direction is going to be down. I have x to the 4th, which means I'm going to have a bouncing root at 0. Undo that. Terrible B. And then I'm going to have a flat root at -5 because of, at -4 because of that x plus 4 to the 5th. So that one's going to be flat. So if my end direction is down, I'm going to start down here, come up, bounce, come back up, and then I'm going to flatten that out and then scooch back up. So my start direction is up, my end direction is down. This is a degree 9 because of that 4 and 5. Let me clarify that 4 and that 5. So that's going to be degree 9 with a leading term of -x to the 9th. I missed this one, -0.1 x to the 8th for that one. So hopefully we're seeing those patterns and understanding how to put those together. Again, we did this chart already, so I'm not going to do it again, but these hold up for higher degree polynomials. All that's the same. If they're odd, they're in opposite directions. If a is negative, they're going down. Yeah, same patterns for the higher degree polynomial. Okay, so a couple things to bring together. The maximum number of roots you could have in a 3rd degree polynomial is 3. Something like that would have 3. Root here, here, and here. They don't all have to have 3. You could have something that goes like this. But we'll get into that later when we talk about imaginary roots. The maximum number of roots an n-degree polynomial could have, so any number, is going to be n. So if I have a 10th degree polynomial, the highest number of roots it could have is 10. For each polynomial function, draw a horizontal line through the graph and state the minimum degree that the equation could have. So I can draw my lines anywhere, but one of the things I'm noticing here is direction changes. So here it'd have 3 degrees. That's the minimum number of degrees I could have. Minimum number of degrees here is 2. Minimum number of degrees here is 4. Minimum here is 5. As I said before, minimum. Yeah, no, that's true. These aren't all going to have, like a 3rd degree polynomial won't always have 3 exact roots or 3 real roots, because we will get into what happens with imaginary roots, but that's not for a little while. All right. So that is 6-1 and 6-2. Sorry, the video went a little bit long. Hopefully it was thorough and you now understand how to draw basic equations and come up with basic equations for higher degree polynomials. Have a good day.